Hello, sleepy genius. The day has asked much of you, and now the night offers stillness in return. Let your breathing slow, your shoulders soften, and your mind drift toward wonder. Tonight, we explore a place where reality bends, where time itself surrenders, and where the universe reveals its most mysterious edge. Rest now, and let curiosity carry you gently into sleep. From the invisible monsters lurking at the centers of galaxies to the point where all known physics unravels into silence, black holes remain the cosmos's deepest enigma. First predicted by equations before anyone believed they could exist, then discovered hiding in plain sight among the stars. These gravitational wells have haunted human imagination since Einstein's pen first traced their theoretical shadows across paper in 1915. Before our journey begins, if these curious facts help you rest and leave a weary day behind, a simple like or subscribe helps others drift here too, one soul at a time. Please share your thoughts below. Now, let's begin. A black hole interior would show you the universe's end accelerated through time dilation. Consider looking outward as you fall through the event horizon, light from the external universe still reaching you. Time dilation effects mean you see external time accelerated, events in the outside universe unfolding faster from your perspective. In principle, you might watch stars live and die, galaxies evolve, perhaps even the universe approach its ultimate fate, compressed into moments. Physicist Andrew Hamilton created simulations in 2008 showing this effect. Though the extreme redshift and blueshifting make actual observation complex, photons gain tremendous energy falling into the potential well alongside you, blueshifting toward gamma rays. The universe behind you might appear as a bright, energetic glow. How much cosmic history you witness depends on the black hole's size and your survival time. To think that falling into darkness offers glimpses of cosmic destiny, future compressed into present through relativistic transformation. A black hole's tidal forces would create different sensations at different depths. Picture the initial gentle stretch as you begin falling, barely noticeable if the black hole is supermassive. As you approach the horizon of a large black hole, you might feel a slight pulling at your extremities, similar to hanging from a bar. Crossing the horizon of Sagittarius A** at 4 million solar masses, you would still feel relatively normal. The tidal forces less than Earth's gravity difference between your head and feet. But deeper inside, approaching the singularity, forces escalate exponentially. Your body would begin stretching noticeably, then painfully, then catastrophically. Physicist Fulvio Melia calculated in 2003 the tidal force profiles inside various black holes. The stretching acceleration reaches thousands of g-forces in the final microseconds before the singularity. To think that darkness provides time for contemplation in massive examples, comfort offered before inevitable destruction. A black hole's quantum effects might create a firewall at the horizon, according to some theories. Imagine approaching the event horizon expecting smooth passage, but instead encountering a wall of high-energy particles that vaporize you instantly. Physicists Ahmad Al-Mahiri, Donald Marolf, Joseph Polchinski, and James Sully proposed in 2012 that preserving quantum information might require violating the equivalence principle, creating this firewall. The idea remains controversial, with some physicists arguing firewalls are artifacts of incomplete understanding rather than physical reality. If firewalls exist, crossing a black hole horizon would be far from the smooth experience general relativity suggests. Alternative proposals invoke quantum entanglement or modifications to information theory to avoid firewalls. The debate continues among theoretical physicists. In a sense, the threshold itself remains contested territory. The boundary between inside and outside, perhaps more dramatic than classical theory suggests. A black hole's interior might connect to a white hole in far future, according to some models. Consider quantum effects causing the black hole interior to tunnel through to a white hole configuration, matter that fell in eventually exploding back out. Physicist Carlo Rovelli and colleagues proposed in 2014 that this transition could occur, though appearing instantaneous externally due to time dilation. From your perspective, falling in, you might experience the black hole interior transforming around you, though what this means for your survival remains unclear. The white hole would eject everything that fell into the black hole, potentially in a distant cosmic epoch. No observational evidence supports this speculative scenario, and it requires quantum gravity effects not yet understood. The mathematics permits such solutions, but whether nature implements them remains unknown. To think that entry might eventually become exit, darkness transforming into explosion across impossible spans of time. A black hole's varying gravity would distort your perception of time during infall. Picture your feet aging faster than your head because they are deeper in the gravitational well, time flowing at different rates across your body. For extreme mass black holes, this effect stays small until very close to the singularity. But for stellar mass holes, it becomes significant. Your feet would experience more proper time than your head during the fall, though the difference remains small in absolute terms. Physicist Kip Thorne explored these time dilation effects, showing how gravity literally creates temporal gradients across extended objects. Your heart might beat slightly faster than your brain processes thoughts. All biological processes running at rates depending on their distance from the singularity. To think that even within one body, time fragments into different streams, a person becoming temporally dispersed across their own height in extreme gravity. A black hole would offer no escape once you crossed the horizon, no matter what technology you possessed. Imagine having access to any engine or device permitted by physics, firing it at maximum power trying to escape after crossing the event horizon. General relativity shows escape is impossible because all future directed paths lead inward. Even a photon rocket approaching perfect efficiency cannot save you, as reaching the horizon requires speed approaching light, and no material object can exceed light speed. Physicist Stephen Hawking proved in the 1970s that horizon crossing is a one-way transition for anything composed of matter or energy. Science fiction often imagines exotic escapes, but mathematics shows otherwise. The event horizon represents not a physical barrier, but a boundary in space-time structure itself. Beyond it, escape means traveling backward in time, which physics forbids. In a sense, the horizon defines true finality, a threshold past which all possibilities collapse into one inevitable future. A black hole could turn you into a hologram encoded on its event horizon according to string theory. Picture your entire three-dimensional body with all its information compressed onto the two-dimensional surface of the event horizon as you fall through. Physicist Leonard Susskind proposed in 1995 that information is never truly lost inside, but remains encoded on the horizon's surface. From an outside observer's perspective, you would appear to spread across the horizon like a projection, your quantum information distributed across the spherical surface. Meanwhile, from your own perspective, you fall through normally experiencing three-dimensional space. This holographic principle suggests reality itself might be a projection from lower dimensional boundaries. Physicist Juan Maldaceni's ADS CFT correspondence in 1997 provided mathematical evidence for holography in certain spacetimes. Your body could simultaneously exist as a volumetric falling object and as a flat encoding on a distant surface. To think that dimension itself becomes ambiguous. Your fate written equally in 3 dimensions, and 2, neither description more real than the other. A black hole's interior might contain negative energy density that violates classical physics. Consider crossing the inner horizon of a charged or rotating black hole where certain quantum field theory calculations suggest the vacuum. Energy becomes negative. Physicist Amos Ory showed in 1991 that even tiny amounts of matter falling through create infinite energy densities at the Cauchy horizon through a process called mass inflation. The gravitational field of infalling matter gets amplified exponentially as it approaches this inner boundary. Your own mass would contribute to this runaway effect, your gravitational energy growing without limit. The region would experience space-time curvature increasing faster than exponentially. Classical black hole interiors might be replaced by these unstable configurations where physics breaks down catastrophically. Theoretical physicist Werner Israel explored these exotic energy conditions in rotating black holes during the 1960s. In a sense, the interior becomes its own apocalypse. Matter destroying space-time structure through unbounded amplification. A black hole could spaghettify you so completely that your atoms form a one-dimensional string. Imagine tidal forces becoming so extreme near a stellar mass black hole's singularity that the distance between atoms in your body exceeds meters, then kilometers. Your body would no longer resemble anything recognizable, transformed into a thread of individual atoms stretched across vast distances. Each atom would be separated from its neighbors by spaces far larger than molecules normally occupy. Physicist John Wheeler contemplated in the 1960s whether matter could be stretched to the point where quantum effects dominate completely. The atoms themselves would eventually be torn apart, but for a brief moment you might exist as a living necklace of separated atoms, consciousness distributed across a cosmic thread. Your final thoughts might propagate along this string of neurons separated by impossible distances, signals taking microseconds to traverse what was once millimeters of brain tissue. To think that a body could become linear, 3-dimensional form flattened to 1 dimension through gravity's relentless pull. A black hole's quantum foam near the singularity might dissolve you into probabilistic uncertainty. Picture approaching the Planck scale, where quantum gravity effects dominate, space-time itself fluctuating wildly at 10 to the power of minus 35 meters. At this scale, physicist John Wheeler proposed in 1955 that space-time becomes a seething foam of quantum fluctuations. Virtual black holes appearing and disappearing. Your particles would not follow definite paths, but exist as probability clouds. The very concepts of position and trajectory lose meaning when space-time coordinates become uncertain. Loop quantum gravity suggests space is quantized into discrete chunks at this scale. Your body might dissolve into quantum superpositions spread across multiple possible geometries simultaneously. Physicist Carlo Rovelli explored how matter behaves when space-time structure itself becomes granular and uncertain. In a sense, you would stop existing as a classical object entirely, becoming a quantum ghost haunting multiple possible geometries, your wave functions smeared across the foam of fluctuating space. A black hole could freeze you in time while simultaneously crushing you from your own perspective. Consider the paradox that external observers see you frozen at the horizon forever while you experience continued fall and destruction. Both perspectives are equally valid in their own reference frames. This means you simultaneously exist in two incompatible states, frozen on the surface and crushed at the center, depending on who observes. Physicist Raphael Boussot explored these complementary descriptions in his work on black hole complementarity in the 1990s. The frozen version of you spreads across the horizon as a hologram, while the falling version reaches the singularity. Quantum mechanics normally prohibits being in two places at once, yet black hole physics seems to require it. No experiment can verify both descriptions simultaneously because no observer can both remain outside and fall in. To think that your fate fragments into incompatible truths, each observer witnessing a different ending. Reality itself unable to agree on what happened to you. A black hole's singularity might not be a point, but a moment in time you cannot avoid. Picture the singularity not as a place in space, but as an instant in your future, unavoidable as next Tuesday. Inside the event horizon, the radial coordinate becomes time-like, while time becomes space-like in the mathematics. Moving toward the singularity is not moving through space, but moving forward through time. Physicist David Finkelstein recognized this coordinate transformation in 1958. You could no more stop yourself from reaching the singularity than you could stop time from advancing. The singularity exists in the future of all world lines inside the horizon. It is not a location you approach, but a moment that approaches you. Your entire remaining lifespan inside the black hole becomes the journey toward this final instant. Every direction you look or move takes you closer to this temporal boundary. In a sense, the singularity is when, rather than where, your death scheduled in space-time coordinates rather than spatial ones. A black hole might contain entire universes in its interior, according to some interpretations. Consider solutions to Einstein's equations where the black hole interior expands into its own infinite space, a separate universe disconnected from the one you left. Physicist Lee Smolin proposed in 1992 that every black hole might spawn a new universe with slightly different physical constants. These baby universes would be completely isolated, no information passing between them and the parent universe. You might fall into a black hole and emerge into an expanding cosmos. The crushing singularity replaced by a big bang-like explosion into new space-time. No observational evidence supports this speculation, but the mathematics permits such solutions. Physicist Nikodem Poplawski showed in 2010 that Einstein-Cartan theory produces such cosmological interiors. To think that darkness might be doorways, each black hole a seed of creation flowering in dimensions perpendicular to our own reality. A black hole could turn you into information that leaks out through quantum entanglement. Picture your quantum state becoming entangled with Hawking radiation particles, escaping the black hole over billions of years. Physicist Leonard Susskind proposed that information about what falls in gradually transfers to outgoing radiation through quantum correlations. Your pattern would be encoded in subtle correlations between photons emitted across eons. Recovering your original quantum state would require collecting and analyzing the entire Hawking radiation output. Physicist Patrick Hayden and John Preskill calculated in 2007 that information emerges surprisingly quickly in the radiation after only half the black hole evaporates. But reassembling a person from these quantum correlations would require technology far beyond known physics. You would be scrambled beyond recognition, your information spread across particles emitted over cosmic timescales. In a sense, you achieve a strange immortality, your essence preserved in quantum correlations but your form destroyed beyond any practical recovery. A black hole's intense gravitational field might create particle-antiparticle pairs from vacuum around you. Consider quantum field theory, predicting that virtual particle pairs constantly appear and annihilate throughout empty space. Near a black hole's intense gravitational field, these virtual particles can become real through the Schwinger effect. The strong tidal forces separate particle and particle pairs before they can annihilate, pulling them apart. You might be surrounded by a fog of electrons and positrons materializing from nothing. Physicist Julian Schwinger first calculated this field-induced pair production in 1951 for electromagnetic fields. Near black hole singularities, gravitational gradients might exceed even the Schwinger threshold. The space around you would sparkle with matter-antimatter creation, vacuum itself becoming luminous. These particles would add their own gravity to the field, creating complex feedback. To think that emptiness becomes fecund near darkness, the void refusing to remain empty when space-time curves beyond critical values. A black hole could stretch the light from your body into infinite wavelengths, making you invisible. Imagine photons leaving your body as you fall, climbing outward against gravity and redshifting toward infinite wavelength. Eventually, the photons become stretched to wavelengths longer than the observable universe, effectively carrying zero energy. From outside perspectives, your image fades, not just to darkness, but to absolute informationlessness. The photons still exist, technically, but convey no detectable signal. Physicist William Unruh analyzed these extreme redshift scenarios in his work on black hole thermodynamics. The last photons to escape before you cross the horizon become infinitely redshifted, their energy approaching zero. Any observer trying to see your final moments would need detectors sensitive to wavelengths approaching infinity. You fade from the universe not through absence, but through your light becoming infinitely diluted. In a sense, you disappear by becoming everywhere and nowhere, your image stretched across all of space, yet invisible. A black hole merger might eject you at relativistic speeds through gravitational slingshot. Consider orbiting one black hole when another passes nearby or merges with it. The changing gravitational field flinging you outward like a stone from a sling. Three-body gravitational interactions near black holes can accelerate objects to significant fractions of light speed. Astrophysicist Jack Hills showed in 1988 that stars can be ejected from galaxies at thousands of kilometers per second through black hole interactions. During merger, the gravitational field becomes highly time-dependent and asymmetric. You might experience acceleration of thousands of g-forces as the field configuration rapidly changes. Some trajectories could accelerate you to 10 or 20% of light speed, enough to cross the galaxy. The acceleration would likely be lethal to biological tissue, crushing organs and rupturing blood vessels. To think that darkness can also expel gravitational chaos, occasionally throwing objects back into the light rather than consuming them. A black hole's electric charge could electrocute you if it somehow maintained net charge. Picture a Reisner-Nordstrom black hole with net electric charge, its field extending outward through space. As you fall toward it, the electric field strength would increase dramatically. If you carry any opposite charge, electromagnetic forces would accelerate you even faster than gravity alone. The electric field near a charged black hole can theoretically exceed any achievable in laboratories. Physicist Hans Reisner and Gunnar Nordstrom derived these solutions in 1916 and 1918. However, astrophysicist Stuart Shapiro showed that real black holes cannot maintain significant charge because they would quickly neutralize by attracting opposite charges from surrounding plasma. A briefly charged black hole might deliver electric shocks millions of times stronger than lightning. Your nervous system would overload instantly, every nerve firing simultaneously. To think that darkness could also shock, electromagnetic fury added to gravitational crushing in these exotic theoretical constructs. A black hole's quantum properties might mean you never truly fall in but hover forever at the horizon from all perspectives. Consider proposals by some physicists that quantum effects create a stretched horizon slightly outside the classical event horizon where infalling matter piles up. Physicist Gerard T. Hooft suggested in 1985 that from any outside observer's perspective, including your own looking at yourself, nothing ever crosses into the black hole. Matter accumulates in a thin shell just outside, quantum mechanically fuzzing the sharp boundary. The classical picture of crossing and falling to singularity might be an idealization that quantum gravity corrects. You would approach arbitrarily close but never quite reach the mathematical horizon. Your subjective experience of crossing might be an illusion, your quantum state actually spreading across the stretched horizon surface. This interpretation remains controversial among physicists. In a sense, the boundary might be absolute even from inside. Entry forbidden by quantum corrections that classical relativity missed. A black hole could trap you in its photon sphere, orbiting at light speed forever, theoretically. Imagine being converted into pure radiation or accelerated to exactly light speed at the photon sphere radius of 1.5 Schwarzschild radii. At this precise distance, photons orbit in circular paths, and theoretically matter at light speed could too. You would circle the black hole eternally, neither falling in nor escaping, frozen in endless orbit. Of course, reaching exactly light speed violates physics for massive particles, and the orbit is unstable, any perturbation dooming you to spiral inward or escape. Mathematician Subrahmanyan Chandrasekhar studied photon orbits extensively in the 1980s, calculating their properties in various black hole spacetimes. The photon sphere creates the inner edge of the black hole's shadow in images. For a brief moment during infall, you might pass through this radius, light from you orbiting the hole multiple times before escaping. To think that there exists a radius where orbiting at light speed becomes possible, though utterly unstable and unreachable for material objects. A black hole's interior might be a gateway to a parallel universe through its ring singularity. Consider that the mathematics of rotating Kerr black holes contains multiple exterior regions connected through the interior. Passing through the ring singularity without touching it might transport you to another asymptotically flat universe with its own stars and galaxies. Physicist Roy Kerr's 1963 solution revealed this structure, shocking the general relativity community. Physicist Roger Penrose drew diagrams in the 1960s showing infinite stacks of universes connected through black hole interiors. However, physicist Amos Ory and others showed these interior passages are likely unstable, collapsing into true singularities due to perturbations. Quantum effects probably destroy the exotic inner structure before you could traverse it. The mathematics dreams of shortcuts between universes, but physics likely forbids them. To think that equations imagine infinite realities nested through darkness, doorways that probably slam shut before anyone could pass through them. Black holes form when massive stars collapse under their own gravity in seconds. Imagine a star 20 times the mass of our sun reaching the end of its life, its nuclear fuel exhausted after millions of years of burning. In less than a second, the core implodes with such violence that protons and electrons merge into neutrons. And then, even that matter surrenders. The star's entire mass compresses into a point of infinite density called a singularity, while the outer layers explode outward in a supernova visible across galaxies. What remains is an object so dense that a teaspoon of its matter would weigh more than Mount Everest. To think that something so catastrophic creates the universe's most perfect geometric forms. The event horizon marks the point of no return around a black hole. Picture an invisible sphere surrounding the singularity, a boundary drawn not in space but in fate itself. Cross this line and every path forward leads only inward. Every future moment points toward the center. For a black hole with the mass of our sun, this boundary would sit just 3 kilometers from the center. While supermassive black holes can have event horizons larger than our solar system, physicist Carl Schwarzschild calculated this radius in 1916 while serving in the German army during World War I, solving Einstein's equations from the trenches. His solution described something so strange that even Einstein doubted such objects could actually exist in nature. This reminds us that the most profound truths sometimes emerge from the most unlikely circumstances. Time itself slows near a black hole's edge due to extreme gravitational time dilation. Imagine watching a friend fall toward the event horizon while you remain safely distant. From your perspective, they would appear to slow down as they approached the boundary, their movements becoming sluggish, their clock ticking slower and slower. At the horizon itself, they would seem to freeze entirely, suspended forever in that final moment. Yet from their perspective, nothing unusual would happen at the horizon crossing, time flowing normally as they plunged inward. Einstein's general relativity, published in 1915, predicted this effect, showing that gravity warps not just space, but time itself. Astronomer Arthur Eddington verified Einstein's theory during a 1919 solar eclipse, though the full implications for black holes took decades to understand. In a sense, every massive object carries its own river of time, flowing at its own pace. The nearest known black hole lies just over 1,000 light-years from Earth. Consider that Gaia BH1, discovered in 2022 by the European Space Agency's Gaia spacecraft, orbits with a Sun-like companion star in the constellation Ophiuchus. Astronomers found it by watching the companion star wobble in its motion, pulled by an invisible partner 10 times the Sun's mass. The system sits close enough that if we could travel at light speed, we would arrive in roughly a millennium. Before Gaia BH1, astronomers believed the closest black hole was much farther, making this discovery feel like finding a sleeping giant in our cosmic backyard. Scientists estimate tens of millions of stellar mass black holes drift through the Milky Way, most completely invisible, betraying their presence only through gravitational effects. To think that such profound darkness hides among the familiar constellations. Spaghettification would stretch your body into a thin stream near a black hole. Picture yourself falling feet first toward a stellar mass black hole. The gravity pulling on your feet far more strongly than your head because your feet are closer to the center. This difference in gravitational force, called a tidal force, would stretch you vertically while compressing you horizontally. For a black hole of 10 solar masses, these tidal forces would become lethal thousands of kilometers before you reached the event horizon, pulling you apart atom by atom. The term spaghettification was coined by physicist Stephen Hawking in his 1988 book, A Brief History of Time. Remarkably, for supermassive black holes millions of times the Sun's mass, the tidal forces at the event horizon are gentle enough that you could cross intact, stretching only becoming extreme much deeper inside. This reminds us that size changes everything, even in the realm of cosmic destruction. Light orbits some black holes in a circular path called the photon sphere. Imagine photons of light trapped in endless circles around a black hole, racing at light speed yet going nowhere, prisoners of curved space-time. This sphere sits 1.5 times farther from the center than the event horizon itself. If you could somehow hover at this precise distance and look tangentially, you would see the back of your own head as light from you circled the black hole and returned. German astronomer Karl Schwarzschild first described this region in 1916, though its full strangeness took decades to appreciate. In 2019, the Event Horizon Telescope captured an image of the black hole in galaxy M87, revealing a bright ring of light, roughly where theory predicted the photon sphere should glow. The ring appeared because matter falling toward the black hole heated to billions of degrees, its light bending around the curved space near the hole. In a sense, we are seeing space-time itself lit from within. Black holes spin at tremendous speeds, measured as angular momentum. Consider that some black holes rotate near the theoretical maximum, their event horizons whipping around hundreds of times per second. This rotation drags space-time itself into a whirlpool, a phenomenon physicists call frame dragging or the Lenz-Thirring effect. Austrian physicists Joseph Lenz and Hans Thirring predicted this in 1918, extending Einstein's equations to rotating masses. The black hole at the center of galaxy NGC 1365, studied in 2013 by NASA's New SDR telescope, spins at 84% of the maximum possible rate. This means spacetime near its equator rotates so violently that nothing could orbit in the opposite direction, swept along like a leaf in a hurricane. To think that emptiness itself can spiral and churn like water in a vortex. Approaching a black hole, you would see the entire future of the universe flash before you. Picture yourself falling toward the event horizon while looking back at the distant stars. Light from those stars would be blue shifted by your acceleration, increasing in frequency and brightness. More remarkably, you would see events unfold faster and faster in the outside universe due to gravitational time dilation working in reverse for incoming light. In the final moments before crossing the horizon, you might witness stars being born and dying, galaxies colliding, perhaps even the end of the universe compressed into an instant. This effect was described theoretically by physicists in the 1960s as they worked out the mathematics of falling into black holes. No one has observed this directly, but the equations suggest an observer falling into certain black holes might see cosmic history accelerate to its conclusion. This reminds us that our perspective shapes not just what we see, but when we see it. The singularity at a black hole's center defies all known physics. Imagine a point of literally zero size containing the entire collapsed mass of a dead star, where density becomes infinite and space-time curvature reaches impossible values. At this point, Einstein's equations produce mathematical infinities, a signal that general relativity itself breaks down. Quantum mechanics might resolve this crisis, suggesting the singularity is not truly a point, but a region of extreme quantum foam, where space and time dissolve into probabilistic chaos. Physicist John Wheeler, who coined the term black hole in 1967, spent decades wrestling with singularities. He believed they represented the boundaries of human knowledge, places where new physics must emerge. String theory and loop quantum gravity both attempt to replace the infinite singularity with something finite but extraordinary. In a sense, singularities are less answers than questions written in the language of mathematics. Stellar mass black holes typically range from 3 to several dozen solar masses. Consider that when a star collapses, it must exceed the Tolman-Oppenheimer-Volkoff limit, of about 3 solar masses to overcome neutron degeneracy, pressure, and form a black hole rather than a neutron star. J. Robert Oppenheimer and Hartland. Snyder published the first theoretical description of stellar collapse to a black hole in 1939. Though the term black hole would not be coined for another 28 years, the most massive stellar black hole discovered in our galaxy, Cygnus X1, weighs approximately 21 solar masses and was the first black hole widely accepted by astronomers when identified in 1971. Astronomers find these objects by watching for X-rays emitted by matter spiraling into them from companion stars. To think that such compact darkness can outweigh dozens of stars, yet occupy a space smaller than a city. Supermassive black holes lurk at the centers of most large galaxies. Picture a monster weighing millions or billions of solar masses, its event horizon stretching wider than entire solar systems. The supermassive black hole at the center of our Milky Way, called Sagittarius A*, weighs approximately 4.1 million solar masses, yet remains invisible except when matter falls into it. In 2022, the Event Horizon Telescope collaboration captured the first direct image of Sagittarius A*, showing the glowing ring of hot gas around the darkness at our galaxy's heart. Even more massive is the black hole in galaxy M87, which weighs 6.5 billion solar masses and was imaged in 2019. How these giants formed remains mysterious, with theories suggesting they grew from stellar black holes that cannibalized surrounding matter over billions of years, or perhaps formed directly from collapsing clouds of gas in the early universe. This reminds us that even at the cosmos's largest scales, darkness anchors light. Intermediate mass black holes remain the most elusive category. Imagine objects weighing hundreds to hundreds of thousands of solar masses, bridging the gap between stellar and supermassive black holes. For decades, astronomers found few convincing candidates, creating a puzzling gap in the mass spectrum. In 2020, the LIGO and Virgo gravitational wave detectors observed the merger of 2 black holes, producing a final black hole of 142 solar masses, the first confirmed intermediate mass black hole. Dense star clusters, called globular clusters, might harbor these mid-sized objects at their cores. Astronomer Carl Gebhardt proposed in 2002 that intermediate mass black holes could form when multiple massive stars collide in the dense centers of young star clusters. Finding more of these objects could reveal how supermassive black holes grew to their tremendous sizes. In a sense, we are missing chapters in the biography of cosmic darkness. Hawking radiation suggests black holes slowly evaporate over time. Consider that quantum mechanics allows particle pairs to spontaneously appear and annihilate near the event horizon. One particle escaping as radiation while its partner falls inward with negative energy. Stephen Hawking proposed this mechanism in 1974. Shocking the physics community by showing that black holes are not truly black, but glow with thermal radiation. For stellar mass black holes, this radiation is incredibly faint, far colder than the cosmic microwave background, meaning they actually absorb more energy than they emit. However, a black hole with the mass of a mountain would radiate at room temperature, while microscopic black holes would explode in bursts of gamma rays. Hawking calculated that a black hole's temperature is inversely proportional to its mass, so smaller black holes radiate faster. This means that in the unimaginably distant future, perhaps 10 to the power of 100 years from now, black holes might be the last structures to fade from existence. To think that even eternal darkness has an expiration date. The information paradox challenges our understanding of quantum mechanics. Picture everything that falls into a black hole, every particle with its unique quantum state, seemingly lost forever as the whole evaporates through Hawking radiation. Quantum mechanics insists information cannot be destroyed. Yet general relativity suggests anything crossing the event horizon is gone, its information crushed into the singularity. Stephen Hawking debated Leonard Susskind and other physicists for decades about this paradox, eventually conceding in 2004 that information might escape through subtle correlations in the Hawking radiation. Physicist Juan Maldaceno's holographic principle suggests information is never truly inside the black hole but encoded on its two-dimensional surface. In 2020, researchers proposed that quantum entanglement between the outgoing Hawking radiation and the black hole's interior might preserve information. This reminds us that the deepest puzzles emerge where our best theories collide. Primordial black holes might have formed in the first second after the Big Bang. Imagine density, fluctuations in the newborn universe so extreme that regions collapsed directly into black holes without needing stars. Physicist Yakov Seldovich and his student Igor Nevikov first proposed this idea in 1966, suggesting microscopic black holes could have formed when the universe was less than a second old. These primordial black holes could range from subatomic masses to thousands of solar masses, depending on when they formed. Some scientists speculate they could constitute some or all of the mysterious dark matter that outweighs visible matter 5 to 1 in our universe. NASA's James Webb Space Telescope and future gravitational wave detectors might find evidence of primordial black holes by observing their gravitational effects. In a sense, black holes might be as old as time itself, witnesses to the first moment of creation. Wormholes might connect distant regions of space through black holes. Consider that Einstein's equations permit solutions where two black holes link through a tunnel in spacetime called an Einstein-Rosen bridge. Einstein and physicist Nathan Rosen described these bridges in 1935, though they showed any such wormhole would collapse too quickly for anything to traverse it. Physicist Kip Thorne explored whether exotic matter with negative energy density might hold a wormhole open long enough for travel, inspiring Carl Sagan's novel Contact. In 2017, physicists proposed that quantum entanglement between black holes might create traversable wormholes at microscopic scales. No evidence suggests macroscopic wormholes exist in nature, and creating one would require technology far beyond current human capabilities. To think that the universe might fold back on itself in ways we can barely imagine. Tidal forces near black holes generate immense heat in surrounding matter. Picture gas and dust spiraling toward a black hole in a flattened disk called an accretion disk. Particles rubbing against each other as inner regions orbit faster than outer ones. This friction heats the material to millions or billions of degrees, causing it to glow across the electromagnetic spectrum from radio waves to X-rays. The accretion disk around the supermassive black hole in galaxy NGC 5548 reaches temperatures of about 2 million degrees Celsius, as measured by NASA's space telescopes. Quasars, the brightest objects in the universe, are supermassive black holes with especially vigorous accretion disks, some shining with the light of 1 trillion suns. Astronomer Donald Lynden Bell proposed in 1969 that quasars were powered by supermassive black holes. This reminds us that destruction can be luminous, that falling into darkness produces the brightest lights in the cosmos. Relativistic jets shoot from some black holes at near light speed. Imagine twin beams of particles and radiation blasting outward from a black hole's poles. extending for thousands of light-years into intergalactic space. These jets form when magnetic fields threading the accretion disk accelerate particles to 99% of light speed or faster, channeling them along the rotation axis. The black hole in galaxy M87 produces a jet visible across 5,000 light-years, first photographed in detail by the Hubble Space Telescope in the 1990s. Radio astronomer Sir Martin Ryle and his colleagues first observed these jets in the 1950s using early radio telescopes, though they did not understand the mechanism. The jet from Quasar 3C 273, discovered in 1963, extends more than 200,000 light-years from its source. In a sense, black holes are not just wells of darkness but also cosmic fountains. Frame-dragging, near-rotating black holes twists space-time into a spiral. Consider that nothing can remain stationary in the ergosphere, a region just outside the event horizon where space-time itself rotates with the black hole. Even light beams would be dragged along in the direction of rotation. Austrian physicist Roy Kerr solved Einstein's equations for rotating black holes in 1963, revealing this bizarre property. The Gravity Probe B satellite launched by NASA in 2004 measured frame dragging around Earth, which spins far too slowly to create an ergosphere but still drags space-time measurably. Near a maximally rotating black hole, the ergosphere extends up to twice the event horizon radius at the equator. Theoretical physicist Roger Penrose proposed in 1969 that energy could be extracted from the ergosphere, a process now called the Penrose process. To think that rotation can grip even the fabric of reality. Binary black holes spiral toward each other, emitting gravitational waves. Picture two black holes orbiting one another, their mutual gravity causing them to lose energy by radiating ripples in spacetime itself. These gravitational waves travel outward at light speed, carrying information about the cataclysm that created them. Einstein predicted gravitational waves in 1916, but thought they would be too weak to ever detect. On September 14, 2015, the LIGO detectors in Louisiana and Washington simultaneously measured gravitational waves from two black holes merging 1.3 billion light-years away, the first direct detection of these elusive ripples. The black holes weighed 36 and 29 solar masses, and when they merged, they converted 3 solar masses of matter into pure gravitational wave energy in a fraction of a second. Rainer Weiss, Kip Thorne, and Barry Barish won the 2017 Nobel Prize in Physics for this discovery. This reminds us that space-time itself can ring like a bell. The no-hair theorem states black holes have only 3 properties. Imagine that no matter how complex the star that collapsed, no matter its chemical composition or magnetic field or shape, the resulting black hole is characterized completely by just mass, electric charge, and angular momentum. Physicist John Wheeler summarized this in the phrase, "Black holes have no hair," meaning they retain no detailed information about their origins. Werner Israel proved in 1967 that non-rotating, uncharged black holes must be perfectly spherical. Brandon Carter extended this in 1971 to rotating black holes, showing they are oblate spheroids. Stephen Hawking and others completed the proof in the early 1970s. This theorem implies that black holes are the simplest macroscopic objects in the universe, yet they emerge from the most violent processes. In a sense, ultimate complexity collapses into ultimate simplicity. Charged black holes would repel other charges with extreme force. Consider a black hole carrying a net electric charge, its event horizon surrounded by an electric field extending into space. Such Reisner-Nordstrom black holes, named after Hans Reisner, and Gunnar Nordstrom, who derived their mathematics in 1916 and 1918, would attract opposite charges and repel like charges. However, astrophysicists believe charged black holes are rare or non-existent in nature because they would quickly neutralize by attracting oppositely charged particles from their surroundings. If a black hole somehow maintained a charge equal to its mass in natural units, it would have no event horizon at all, exposing a naked singularity forbidden by Roger Penrose's cosmic censorship hypothesis. The mathematics describing charged black holes reveals inner and outer horizons with a region between where peculiar physics allows closed time-like curves. To think that charge could transform a black hole into something even stranger. White holes are the time-reversed twins of black holes, in theory. Picture a region of space-time that cannot be entered from outside, but only exited, the opposite of a black hole. White holes emerge mathematically when physicists reverse the time coordinate in the equations describing black holes. While black holes represent gravitational collapse, white holes would represent gravitational explosion, spewing matter and energy outward. No evidence suggests white holes exist in nature, and most physicists believe they are mathematical curiosities rather than physical objects. Some cosmologists have speculated that the Big Bang itself might have been a white hole, the ultimate explosion from a singularity. In 2014, physicist Hal Haggard and Carlo Rovelli proposed that black holes might transform into white holes through quantum effects, though this remains highly speculative. This reminds us that equations sometimes dream of impossible things. Gravitational lensing allows black holes to bend light from background stars. Imagine light from a distant star passing near a black hole, its path curved by the warped space-time around the hole. This can create multiple images of the star, distorted arcs, or even complete rings of light, called Einstein rings. Astronomers use this effect to detect black holes that are not actively accreting matter and thus emit no light themselves. In 2011, astronomers observed a lone star passing behind Sagittarius A*, the Milky Way's central black hole, allowing them to measure the hole's mass precisely from how it bent the star's light. Fritz Zwicky first proposed using gravitational lensing to study cosmic objects in 1937, though the technology to observe it took decades to develop. Einstein himself calculated the lensing effect in 1936, but doubted it would ever be observable. In a sense, darkness makes itself known by bending light. Micro-black holes could theoretically exist, but would evaporate almost instantly. Consider a black hole with the mass of an asteroid or smaller, its event horizon measured in micrometers or less. Such objects would radiate Hawking radiation intensely, their small mass giving them high temperature. A black hole with the mass of a car would evaporate in about 10 to the power of -80 seconds, far faster than any known physical process. Some physicists worried that the Large Hadron Collider near Geneva might accidentally create micro-black holes in high-energy particle collisions, but calculations showed any such holes would evaporate harmlessly in immeasurably brief instants. Stephen Hawking published detailed calculations of micro-black hole evaporation in 1975, showing they would end their lives in explosions of gamma rays and elementary particles. To think that the smallest black holes would burn the brightest. Quasistars might have been black holes inside living stars in the early universe. Picture a star thousands of times the mass of the Sun with a black hole at its core. The hole slowly consuming the star from within while the star's immense gravity keeps it together. Astrophysicists proposed in 2007 that such objects might have formed in the first billion years after the Big Bang, when gas clouds were denser and more pristine. The black hole would power the star by converting infalling matter into radiation, making the star shine far brighter than fusion alone could sustain. These hypothetical quasistars could grow black holes to thousands or millions of solar masses in just a few million years, potentially explaining how supermassive black holes appeared so early in cosmic history. Computer simulations by researchers at the University of California suggest quasistars could have existed briefly before collapsing entirely. This reminds us that the boundary between star and black hole might sometimes blur. The Schwarzschild radius defines where the event horizon forms. Imagine compressing any object until its escape velocity equals the speed of light. That critical radius is its Schwarzschild radius. For Earth, this radius is about 9 millimeters, meaning if you could compress our entire planet into a sphere smaller than a marble, it would become a black hole. For the Sun, the Schwarzschild radius is about 3 kilometers. Karl Schwarzschild derived this while serving on the Russian front in World War I, sending his solution to Einstein in late 1915, just months after Einstein published General Relativity. The formula is simple. The Schwarzschild radius equals twice the object's mass times Newton's gravitational constant divided by the speed of light squared. Schwarzschild died of a skin disease in 1916 at age 42, never knowing his solution would become foundational to black hole physics. In a sense, every object shadows a black hole within, revealed only by sufficient compression. Sagittarius A** was confirmed through decades of tracking stellar orbits. Consider that astronomers mapped stars orbiting the Milky Way's center for more than 25 years, watching them trace elliptical paths around an invisible point. The star S2 completes an orbit every 16 years, reaching speeds up to 3% of light speed at its closest approach. In 2020, the gravity instrument on the Very Large Telescope in Chile measured S2 passing within 120 astronomical units of Sagittarius A**, about 4 times Neptune's distance from the Sun, confirming general relativity's predictions in the strong gravitational field. Reinhard Genzel and Andrea Ghez led these observational campaigns starting in the 1990s, earning the 2020 Nobel Prize in Physics for their work. The observations proved that a compact mass of 1 million solar masses occupies a region smaller than Mercury's orbit. To think that watching stars dance reveals the invisible partner leading them. Black hole mergers can produce gravitational wave chirps audible to human ears. Picture the final moments as 2 black holes spiral together, their orbital frequency increasing from once per hour to thousands of times per second. The gravitational waves they emit sweep upward in frequency and amplitude like a bird's chirp. LIGO scientists converted the gravitational wave signal from the first detected merger into sound waves, creating an audible chirp lasting a fraction of a second. The frequency sweeps from about 35 Hz to 250 Hz, within the range of human hearing. Physicist Kip Thorne predicted in the 1980s that such mergers would produce these distinctive chirps, allowing scientists to identify black hole collisions instantly. More than 90 gravitational wave events from black hole mergers have been detected since 2015, each with its unique chirp revealing the masses and spins of the merging holes. This reminds us that the universe has a voice, if only we build the ears to hear it. Naked singularities would violate cosmic censorship if they existed. Imagine a singularity without an event horizon, its infinite curvature and density visible to the outside universe. Roger Penrose proposed the cosmic censorship hypothesis in 1969, conjecturing that nature forbids such naked singularities from forming. If they existed, They would create regions where general relativity's equations produce unpredictable results, allowing effects to propagate without clear causes. Some solutions to Einstein's equations permit naked singularities under contrived conditions, such as non-spherical collapse or rapidly rotating charged black holes. In 1991, physicists Stuart Shapiro and Saul Tucholsky ran computer simulations suggesting that rapidly spinning, collapsing stars might briefly create naked singularities before settling into normal black holes. Proving cosmic censorship mathematically remains one of the great unsolved problems in general relativity. In a sense, the hypothesis suggests the universe is modest, always veiling its most extreme features. Time appears to stop at the event horizon from an outside perspective. Consider watching an object fall toward a black hole, its image becoming dimmer and redder as it approaches the horizon. The light from the object takes longer and longer to reach you as it originates from deeper in the gravitational well. Mathematically, it takes infinite time for the object to cross the horizon as measured by your distant clock. Yet the object's own clock shows it crossing in finite time, with nothing special happening at the horizon itself for small enough black holes. This discrepancy troubled early researchers until they realized the event horizon is an observer-dependent feature, a boundary in spacetime rather than a physical barrier. David Finkelstein introduced coordinates in 1958 that removed the mathematical singularity at the event horizon, showing it was an artifact of poor coordinate choices. To think that one surface can mean something completely different depending on where you stand. Quasi-periodic oscillations reveal black holes devouring stars. Picture a star torn apart by tidal forces as it wanders too close to a supermassive black hole. Its gas falling inward in a chaotic stream that eventually settles into an accretion disk. Sometimes this disk oscillates with nearly regular periods, producing brightness variations every few hours or days. Astronomers detected such oscillations from the X-ray binary GRS 1915 + 105 in 1997, with periods of about 67 Hz, suggesting they arise near the innermost stable circular orbit around the black hole. These oscillations provide a way to measure black hole spin because the innermost stable orbit depends on rotation. In 2015, astronomers observed quasi-periodic oscillations in X-rays from a supermassive black hole shredding a star in galaxy PGC 043234. The oscillations revealing the black hole's mass and spin. This reminds us that even in death's throes, matter carries information. The photon sphere creates shadow effects visible in black hole images. Imagine light trying to orbit a black hole at the photon sphere, any slight inward perturbation causing it to spiral into the horizon, any outward one allowing it to escape. This creates a circular shadow slightly larger than the event horizon itself, a dark disk where almost no light emerges. The Event Horizon Telescope images of M87 and Sagittarius A** show this shadow surrounded by a bright ring from the accretion disk. For M87's black hole, the shadow spans about 42 billion kilometers, or 280 times the distance from Earth to the Sun. Theoretical physicist Jean-Pierre Luminet created the first accurate simulation of a black hole's visual appearance in 1979, predicting the bright ring and central shadow. The match between these 1979 predictions and the 2019 observations validated general relativity in the extreme environment near a supermassive black hole. In a sense, darkness has a diameter. Gravitational redshift stretches light climbing out of deep gravitational wells. Consider a photon of light emitted near a black hole's event horizon, struggling against gravity to escape. As it climbs outward, it loses energy, its wavelength stretching toward the red end of the spectrum. Light emitted from just above the event horizon would be redshifted so severely that it becomes undetectable, fading into infrared and beyond. This effect, predicted by Einstein's general relativity, has been measured around white dwarfs and neutron stars. In 2018, astronomers detected gravitational redshift in light from gas clouds orbiting within a few light hours of Sagittarius A*, showing that the clouds sit deep in the black hole's gravitational well. The gravity instrument measured the redshift combined with transverse Doppler shift as clouds whipped around the black hole at 3% of light speed. To think that photons remember the depths from which they climbed. Accretion disk winds blow matter away from black holes at tremendous speeds. Picture hot gas in the inner accretion disk being lifted by magnetic fields and radiation pressure, accelerating outward in winds reaching thousands of kilometers per second. These winds can remove more matter than falls into the black hole, regulating the hole's growth. Astronomers using NASA's Chandra-X Observatory observed winds from the supermassive black hole in galaxy PDS 456 reaching 30% of light speed in 2015, carrying away more mass per year than forms in new stars throughout the galaxy. Such winds might explain why supermassive black holes and their host galaxy bulges follow tight correlations in mass, the holes limiting their own growth by blowing away surrounding gas. Theoretical astrophysicist Mitchell Bagelman modeled accretion disk winds in the 1980s, showing how radiation pressure could drive powerful outflows. This reminds us that black holes both devour and expel, judges of what matter may approach. The innermost, stable, circular orbit marks a point of no return for orbiting matter. Imagine trying to orbit a black hole ever closer to the event horizon, eventually reaching a radius where no stable orbit exists, no matter how fast you move. For a non-rotating black hole, this radius sits at 3 times the Schwarzschild radius. Inside this boundary, any orbit will either spiral inward or escape outward. For rotating black holes, the innermost stable orbit can be much closer if orbiting in the direction of rotation, as close as the event horizon itself for maximally spinning holes. This region produces the brightest X-ray emission from accretion disks as matter plunges inward from the innermost stable orbit. Astrophysicist James Bardeen calculated these orbits in 1972, showing how they depend on black hole spin. In a sense, even circular motion has limits in the most curved regions of space. Tidal disruption events occur when stars pass too close to supermassive black holes. Consider a star wandering near a galaxy's central black hole, tidal forces stretching it into a long stream of gas once it crosses the tidal radius. Half the star's mass typically falls back toward the black hole over months or years, producing a bright flare of light as it forms an accretion disk. Astronomers have observed dozens of these events in distant galaxies, each producing a characteristic brightening and fading. In 2019, the Zwicky Transient Facility detected a tidal disruption event in Galaxy 2 MASX J07001137, 6,602,251, watching the supermassive black hole there devour about half a solar mass of stellar material. These events occur roughly once every 10,000 years per galaxy. Astrophysicist Martin Rees analyzed tidal disruption in detail in 1988, predicting the light curves observers would see. To think that stars sometimes pay the ultimate price for wandering too near the edge. Gravitational slingshots can accelerate objects to tremendous speeds near black holes. Picture a star in a binary system with a black hole, its companion orbiting close enough to transfer mass. Another star passing nearby could gravitationally interact with the binary, gaining energy and being flung outward at high velocity. Some hypervelocity stars in our galaxy, traveling fast enough to escape the Milky Way's gravity, might have been accelerated by the supermassive black hole at the galactic center. In 2005, astronomer Warren Brown discovered a star moving at 850 kilometers per second, fast enough to leave the galaxy in about 200 million years. The star likely was once in a binary system that wandered too close to Sagittarius A*, one star captured while the other was flung away. Computer simulations show that three-body interactions near black holes can accelerate objects to relativistic speeds. This reminds us that darkness can throw as well as catch. Black hole bombs could extract energy through superradiance. Imagine a black hole surrounded by a mirror-like shell reflecting waves back toward the hole. Certain waves striking a rotating black hole can extract rotational energy and amplify, bouncing between the hole and the mirror in a runaway process. Physicist Roger Penrose proposed a classical version of this in 1969, and physicist Yakov Seldovich extended the idea to waves in 1971. Predicting that rotating black holes would amplify electromagnetic or gravitational waves with the right frequencies. If a massive field existed naturally around a black hole, like a cloud of ultralight particles, it could form a gravitational atom and extract energy through superradiance without needing an artificial mirror. Physicists have proposed using this effect to search for ultralight dark matter particles that might form clouds around spinning black holes. In a sense, rotation is a form of stored energy waiting for the right key to unlock it. Optical vortices might form in the accretion disks of black holes. Consider turbulent flows in the hot gas spiraling toward a black hole, creating whirlpools and eddies like water flowing down a drain, but governed by magnetic forces and relativistic speeds. These vortices can trap and redirect magnetic field lines, affecting how matter falls inward and how jets launch outward. Computer simulations of accretion disks performed at the Institute for Advanced Study in 2018 revealed complex vortex structures forming and dissipating on timescales of hours near stellar mass black holes. The vortices generate flickering in X-ray emission, explaining some of the rapid variability observers see from active black holes. Physicist Stephen Balbus and astronomer John Hawley developed the theory of magnetorational instability in 1991, showing how magnetic fields destabilize smooth disk flows and create turbulent structures. To think that even in the final descent, matter swirls and rebels before surrendering. Gravitational wave memory could leave permanent space-time distortions after black hole mergers. Picture two massive black holes colliding and merging, the cataclysm sending powerful gravitational waves outward through the universe. After the waves pass, space-time does not return exactly to its original shape, but retains a permanent offset, a memory of the violent event. This effect, predicted by Yakov Seldovich and Alexander Polnarev in 1974, would appear as a lasting change in the separation between test masses even after the oscillating gravitational waves have passed. The effect is subtle, perhaps 10,000 times smaller than the wave amplitude itself, making it extremely difficult to detect. Physicists proposed in 2017 that pulsar timing arrays might detect gravitational wave memory from supermassive black hole mergers across the universe. Future detectors, like LISA, the Laser Interferometer Space Antenna planned for the 2030s, might measure this effect directly. This reminds us that the universe keeps scars from its most dramatic moments. Black holes might create baby universes through quantum tunneling. Imagine the singularity at a black hole's center, not as an endpoint, but as a gateway. A region where quantum effects allow space-time to tunnel into a separate universe, disconnected from our own. Some solutions to the equations of quantum gravity suggest this possibility. With the new universe expanding away from the black hole's singularity into its own space and time. Physicist Lee Smolin proposed in 1992 a theory of cosmological natural selection where black holes create new universes with slightly different physical constants, potentially explaining why our universe's laws seem fine-tuned for complexity. No observational evidence supports this speculative idea, and it remains unclear whether physics even permits such tunneling. In 2014, theoretical physicists showed that if baby universes form, they would be forever isolated from the parent universe with no possibility of communication. In a sense, every black hole might be a seed of creation, flowering in dimensions we cannot see. Disk instabilities can cause black hole accretion to vary on many timescales. Consider that the flow of matter into a black hole is rarely smooth and steady, but fluctuates due to turbulence, magnetic reconnection, and thermal instabilities in the accretion disk. Some black hole systems show outbursts where brightness increases by factors of thousands or millions as instabilities suddenly dump large amounts of matter inward. The black hole binary system V404 Cygni underwent a dramatic outburst in June 2015, its brightness varying wildly from hour to hour as observers worldwide tracked the event. Such outbursts occur when matter accumulates in the outer disk until density and temperature rise enough to trigger a thermal instability that propagates inward. Astrophysicists Donald Lynden Bell and John Pringle developed the theory of disk instabilities in the 1970s. These variations make black holes some of the most dynamic objects in the universe, never twice appearing exactly the same. To think that even hunger has its rhythms. Quasistellar objects called blazars point their jets directly at Earth. Picture a supermassive black hole with relativistic jets shooting from its poles, one jet aimed almost precisely toward our planet. The jet's particles moving near light speed create extreme relativistic beaming, amplifying the brightness we observe by factors of thousands. Blazars are among the most variable objects in the sky, brightening and dimming on timescales from years down to minutes. The blazar Markarian 421, about 400 million light-years away in the constellation Ursa Major, varies dramatically in gamma-ray brightness observed by NASA's Fermi telescope. Astronomer Edward Spiegel coined the term blazar in 1978, combining BL Lacertae objects and quasars into one category. In 2018, the IceCube neutrino detector in Antarctica traced a high-energy neutrino back to the blazar DX S0500 6+0 proving that blazars accelerate particles to extraordinary energies. Orientation matters, that facing something directly changes everything we see. Eddington luminosity sets a limit on how fast black holes can grow. Imagine a black hole accreting matter so rapidly that radiation pressure from the infalling material pushes outward with the same force that gravity pulls inward. This balance point, called the Eddington limit, restricts how quickly matter can fall into the hole. For a black hole of one solar mass, the Eddington luminosity equals about 30,000 times the Sun's output. British astrophysicist Arthur Eddington described this limit in 1926 while studying stellar structure, though it applies equally to accreting black holes. Some objects called ultraluminous X-ray sources appear to exceed their Eddington limits, possibly through beamed emission or by having intermediate mass, black holes larger than initially estimated. Observations in 2014 of pulsar M82X2 showed it shining at 100 times its Eddington limit, challenging theoretical understanding. In a sense, there is a speed limit to devouring, enforced by the very light that destruction creates. Gravitational waves from black hole mergers carry away enormous energy. Consider that when two black holes spiral together in their final moments, they radiate gravitational waves with a peak power exceeding the combined light output of all stars in the observable universe. The first detected merger released about 3 solar masses worth of energy as gravitational waves in a fraction of a second. More energy than all the stars in the visible universe emitted as light during that same instant. These waves ripple outward at light speed, stretching and squeezing space-time by amounts smaller than an atomic nucleus over kilometer-scale distances. The LIGO detectors measure these tiny distortions using laser interferometry accurate to a 10,000th the width of a proton. Physicist Joseph Weber attempted to detect gravitational waves using large aluminum cylinders in the 1960s, but the technology proved insufficient. To think that colliding darkness briefly outshines all the cosmos's light combined. Optical depth in accretion disks affects what radiation escapes. Picture photons generated deep within a thick accretion disk, scattering off electrons and atoms countless times before potentially reaching the surface. In optically thick disks, radiation diffuses outward slowly, thermally coupled to the gas. The disk's temperature and spectrum depend on how efficiently radiation escapes versus being trapped. Thin disks around stellar mass black holes can be optically thin, allowing X-rays to emerge directly from hot regions. Astrophysicist Nikolai Shakura and physicist Rashid Sunyaev developed the influential alpha disk model in 1973, parameterizing the viscosity that allows matter to spiral inward while radiation escapes. Observations with space-based X-ray telescopes revealed that real accretion disks show more complexity than simple models predicted, with coronae of hot gas above the disk surface. This reminds us that even in destruction's machinery, light must find its path. Black hole binaries can recoil from mergers like a fired cannon. Imagine two black holes with different masses or spins colliding asymmetrically. The gravitational waves carrying momentum away, preferentially in one direction. Conservation of momentum requires the merged black hole to recoil in the opposite direction, potentially at speeds of thousands of kilometers per second. Simulations by physicist Carlos Busto and colleagues in 2007 showed that optimal configurations could produce kicks exceeding 5,000 kilometers per second, fast enough to eject the merged hole from even massive galaxies. Astronomers discovered a possible example in galaxy CID 42, where X-ray and optical observations in 2012 suggested a supermassive black hole displaced from its galaxy's center by 3,000 light-years. These recoiling black holes could wander into galactic space, orphaned from their birth galaxies. In a sense, even the merger of titans produces recoil, action, and reaction written into space-time itself. Magnetic fields can launch jets through the Blandford's-Nyack mechanism. Consider magnetic field lines threading through a rotating black hole's event horizon, the hole's rotation twisting these fields and extracting rotational energy. Astrophysicists Roger Blandford and Roman Znayak described this process in 1977, showing how rotating black holes could power jets without matter needing to cross the horizon. The magnetic fields act like transmission lines carrying electromagnetic energy from the hole's rotation to the surrounding space. The mechanism works most efficiently for rapidly spinning black holes with strong magnetic fields anchored in the accretion disk. Simulations in 2020 by astrophysicists at the University of Amsterdam showed the Blandford's-Nyack process could power jets like those observed from M87's supermassive black hole. To think that rotation and magnetism conspire to turn darkness into cosmic fountains. Extreme mass ratio inspirals occur when stellar mass objects orbit supermassive black holes. Picture a small black hole or neutron star spiraling into a supermassive black hole over thousands of orbits, each loop taking it slightly closer. These systems emit gravitational waves in a complex pattern that encodes detailed information about both objects and tests general relativity in the strong field regime. The small object acts like a probe, mapping the spacetime around the supermassive hole. Future space-based detectors like LISA will observe these in-spirals from millions or billions of light-years away. Astrophysicist Scott Hughes calculated in 2000 that LISA could detect extreme mass ratio in-spirals and extract precise measurements of supermassive black hole masses and spins. The gravitational wave signal from one complete in-spiral could last months or years. This reminds us that sometimes the small reveals the large, a tiny dancer illuminating the giant around which it whirls. Cosmic censorship might fail in higher dimensions beyond our four-dimensional space-time. Imagine universes with 4 space dimensions and 1 time dimension, where black holes have different properties than in our universe. Physicists studying string theory and higher dimensional gravity found in 2002 that naked singularities could form more easily in 5 or more dimensions. Roberto Emperin and Harvey Reel discovered black rings in 2001. Donut-shaped black holes possible only in 5 or more dimensions. These exotic objects can have the same mass and angular momentum as spherical black holes but different horizon geometries, violating uniqueness theorems that hold in 4 dimensions. Whether higher dimensions exist in nature remains unknown, though string theory requires them. In a sense, the rules that govern darkness might change in realms beyond our perception. Fuzzballs might replace singularities if string theory is correct. Consider that, instead of a point singularity, the interior of a black hole could be filled with a dense tangle of strings and brains, forming a fuzzball that has no singularity at all. String theorist Samir Mather proposed this idea in 2003, suggesting that quantum effects at the horizon scale eliminate the classical singularity. In this picture, the event horizon is not a sharp boundary but a fuzzy quantum region where strings form an incredibly complex structure. The fuzzball would have the same mass and charge as the classical black hole and look identical from far away. This might resolve the information paradox by storing information in the fuzzball structure rather than destroying it at a singularity. No observational tests can yet distinguish fuzzballs from classical black holes. To think that infinite density might soften into quantum tangles, intermediate luminosity optical transients might be tidal disruption events of white dwarfs. Picture a white dwarf star wandering too close to an intermediate mass black hole, tidal forces ripping the dense stellar remnant apart. The disruption would be more violent than for normal stars, producing a characteristic explosion visible across millions of light-years. Astronomers observed such an event in galaxy NGC 3599 in 2010. The brightening consistent with a white dwarf being shredded by a black hole of several thousand solar masses. The white dwarf's compact size means it must get very close to the black hole before disruption, producing different observational signatures than normal stellar disruptions. Theoretical work by astrophysicist Clement Bonnerat in 2016 showed that white dwarf disruptions could help astronomers find intermediate mass black holes. This reminds us that even stellar corpses can illuminate the darkness that consumes them. Electromagnetic cascades near black holes create pair production halos. Consider gamma rays near a black hole colliding with each other, their energy converting into electron-positron pairs according to Einstein's mass-energy equivalence. These particles can emit more gamma rays through inverse Compton scattering, creating cascades. The process generates a glow of electrons and positrons around active black holes. Astrophysicist Julian Krolik described these cascades in 1999, showing they affect the spectra of radiation escaping from black hole environments. Observations of gamma rays from blazars by the Fermi Space Telescope revealed signatures consistent with pair production cascades. The effect becomes especially important near magnetized black holes, where charged particles accelerate to extreme energies. In a sense, light transforms into matter and back again in an endless dance near the horizon. Precession of orbits around rotating black holes creates complex patterns. Imagine an orbit that doesn't close on itself, but rotates slowly, the orbit's perihelion advancing with each circuit. This frame-dragging effect is much stronger near black holes than the orbital precession Mercury exhibits around the Sun. The star S to orbiting Sagittarius A** shows measurable orbital precession. Its ellipse rotating about 12 arc-minutes per orbit due to both general relativistic effects and the gravitational influence of other matter near the black hole. Gravity collaboration observations in 2020 detected this Schwarzschild precession, confirming general relativity's predictions. For closer orbits, precession becomes more dramatic, the orbit tracing flower petal patterns. Astrophysicist Clifford Will calculated in 2008 that observing orbital precession precisely could measure black hole spins. To think that orbits remember the spin of the darkness they encircle. Thick accretion disks called tori can form around rapidly accreting black holes. Consider gas falling inward so quickly that radiation cannot escape efficiently, trapping heat and causing the disk to puff up into a fat donut shape. These thick disks, first modeled by astrophysicist Marek Abramovich in the 1980s, can have complex flows including convection and meridional circulation. The thick disk's inner edge hovers above the black hole, matter plunging inward from there in nearly radial trajectories. These structures might form during tidal disruption events or in the most rapidly growing supermassive black holes in the early universe. Simulations show that thick disks are unstable to various perturbations, possibly explaining rapid variability in some accreting systems. In a sense, gluttony breeds instability even in the realm of black holes. Quasinormal modes are the characteristic vibrations of perturbed black holes. Picture a black hole struck by infalling matter or merging with another hole, the impact making the horizon ring like a struck bell. The oscillations decay over time as gravitational waves carry away the energy, with frequencies and damping times determined entirely by the hole's mass and spin. Astrophysicist Subramanian Chandrasekhar and physicist Sol Tucholsky developed the mathematical framework for these modes in the 1970s and 1980s. LIGO has observed quasinormal mode ringing in the gravitational wave signals following black hole mergers. The ring-down phase lasting milliseconds for stellar mass holes. These observations provide direct tests of the no-hair theorem. In 2019, physicists analyzed the ring-down from multiple detectors, confirming the spectrum of overtones matched general relativity's predictions. This reminds us that even space-time has a voice. singing in frequencies unique to curved geometry. Bondi accretion describes how black holes consume surrounding gas in simple scenarios. Imagine a black hole sitting in a uniform, static gas cloud, gravity pulling the gas inward in steady spherical flow. British mathematician Hermann Bondi worked out the mathematics in 1952. Decades before black holes were confirmed, the accretion rate depends on the gas density and temperature far from the hole, with hotter gas accreting more slowly because thermal pressure resists gravity. Real astrophysical environments rarely match Bondi's idealized assumptions, with rotation, magnetic fields, and turbulence complicating the picture. Nevertheless, Bondi accretion provides a useful baseline for understanding more complex flows. Observations of Sagittarius A** suggest it accretes far less efficiently than Bondi predicted, perhaps because strong winds blow most matter away before it reaches the horizon. To think that even the simplest feeding has its complications. Spin-flip transitions can occur when binary black holes merge with misaligned spins. Consider two black holes orbiting each other with rotation axes pointing in different directions, their spins misaligned with the orbital angular momentum. As they spiral inward and merge, gravitational torques can suddenly flip the final black hole's spin direction by large angles. Simulations by physicist Davide Gerosa in 2015 showed that spin flips of up to 180 degrees can occur, the merged hole spinning in a completely different direction than either progenitor. These flips affect the direction of any jet that forms after the merger. Observing many mergers with LIGO could reveal whether black hole spins in binaries are randomly oriented or preferentially aligned. In a sense, collision is transformation, identity lost and reborn in new configuration. Photon rings could appear in higher resolution black hole images. Picture light from the accretion disk, making 1, 2, or more complete orbits around the black hole before escaping, creating nested rings of light progressively closer to the photon sphere. Each ring is an exponentially demagnified image of the accretion disk from a slightly different angle. Astrophysicist Samuel Graller calculated in 2019 that the Event Horizon Telescope's current resolution shows only the direct emission and the first photon ring blended together. Future arrays with baselines extending into space could resolve the second and higher photon rings. These rings encode information about the black hole's mass, spin, and the space-time geometry near the horizon. In 2020, physicists showed that measuring multiple photon rings could test general relativity with unprecedented precision. To think that light circles darkness like memories orbiting loss. Black hole complementarity suggests information appears to both escape and fall in. Imagine watching a particle fall into a black hole. From your distant perspective, the information spreads across the event horizon as Hawking radiation slowly evaporates the hole. Meanwhile, from the particle's perspective, it falls cleanly through the horizon with no drama. Physicist Leonard Susskind proposed in 1993 that both descriptions are valid and complementary, like wave-particle duality in quantum mechanics. No single observer can verify both perspectives simultaneously, preventing paradox. This controversial idea suggests the event horizon has observable features from outside but remains smooth when crossed. Physicist Don Page and others challenged complementarity, arguing it might violate quantum mechanics in subtle ways. The debate continues in the physics community. This reminds us that reality itself might depend on perspective, truth fracturing into complementary facets. Magnetohydrodynamic simulations reveal turbulent accretion disk structures. Consider the complex interplay of gas pressure, magnetic tension, and gravity in accretion flows, captured in computer simulations requiring millions of processor hours. These simulations by research teams at institutions like the Princeton Institute for Advanced Study and University of Illinois show magnetic field loops rising from the disk, reconnecting and releasing energy. The magnetorotational instability discovered by Balbus and Hawley creates turbulence that allows matter to lose angular momentum and spiral inward. Three-dimensional simulations in 2003 first captured the full complexity of MHD turbulence in accretion disks. More recent simulations incorporate general relativity, following gas from hundreds of Schwarzschild radii down to the event horizon. To think that chaos is the path matter follows toward oblivion. Firewalls might incinerate anything crossing a black hole's event horizon. Picture the horizon not as a smooth surface, but as a wall of high-energy particles and radiation that would vaporize any infalling matter. Physicists Ahmed Al-Mehri, Donald Moralf, Joseph Polchinski, and James Sully proposed this idea in 2012 to resolve contradictions between black hole complementarity and quantum mechanics. The firewall paradox suggests that preserving quantum information requires breaking the equivalence principle. Einstein's assertion that freefall is locally indistinguishable from floating in empty space. Some physicists argue firewalls don't exist, and the paradox reveals gaps in our understanding. Others suggest quantum entanglement between early and late Hawking radiation could eliminate the need for firewalls. The debate reshaped how physicists think about quantum gravity and black holes. In a sense, the question of what lies at the horizon reveals cracks in our deepest theories. Optical interferometry could eventually image Sagittarius A**'s photon ring in detail. Imagine connecting optical telescopes across continents or even in space, creating a virtual telescope with resolution far exceeding what radio interferometry achieves. Such an array could potentially resolve structures smaller than the gravitational radius of Sagittarius A**. Astronomer Shepard Dolman, who led the Event Horizon Telescope project, proposed extending interferometry to shorter wavelengths to achieve higher resolution. The atmosphere interferes with optical interferometry from the ground, so space-based arrays might be necessary. In 2020, researchers proposed the Event Horizon Explorer mission concept to place multiple satellites in Earth orbit for this purpose. Such observations could test general relativity in unprecedented detail and directly image the photon sphere structure. To think that human ingenuity might someday count the rings of light encircling darkness. Colliding black holes can produce gravitational wave echoes if exotic structures exist. Consider gravitational waves reflecting off structure near the event horizon, creating echoes that arrive slightly after the main signal. Physicist Jyotirbedi and colleagues claimed in 2017 to find hints of echoes in LIGO data, though other researchers dispute these findings. Echoes would indicate deviations from general relativity or the presence of exotic physics at the horizon scale, such as fuzzballs or gravastars. The lack of confirmed echoes in most analyses supports the idea that black holes match classical predictions. Future gravitational wave detectors with better sensitivity might definitively confirm or rule out echo signals. In a sense, silence itself contains information. What doesn't echo back, revealing surfaces that swallow all. Gravitational waves could reveal primordial black holes from the early universe. Picture black holes formed not from stellar collapse, but from density fluctuations in the first fraction of a second after the Big Bang, potentially ranging from asteroid mass to thousands of solar masses. If primordial black holes constitute some fraction of dark matter, LIGO and future detectors might observe their mergers with distinctive characteristics, different from stellar black holes. Researchers at Caltech analyzed gravitational wave data in 2016, looking for evidence that the detected black holes were primordial rather than stellar in origin. The mass distribution and merger rates could distinguish between the two populations. Observations from NASA's James Webb Space Telescope of early galaxies might also reveal signatures of primordial black hole seeds. To think that darkness from the universe's first moment might still drift among us. Plasma effects near black holes can create radio emission through synchrotron radiation. Imagine electrons spiraling along magnetic field lines in the accretion flow, their acceleration producing radio waves that carry energy away from the system. This synchrotron emission makes many black holes detectable through radio telescopes, despite their inherent darkness. The radio spectrum reveals information about magnetic field strength and electron energy distribution. Sagittarius A** flickers in radio emission on timescales of minutes, suggesting turbulent variations in the accretion flow. Astronomer Robert Brown and colleagues first detected radio emission from Sagittarius A* in 1974. Though they did not immediately realize they had found the galaxy's central black hole. The Very Large Array in New Mexico has monitored its radio variability for decades. This reminds us that even in silence, darkness speaks through the matter spiraling toward it. Retrograde accretion occurs when matter orbits opposite to a black hole's spin. Consider gas falling toward a rotating black hole from a direction that carries it backward relative to the hole's rotation. This retrograde matter experiences stronger tidal forces and less centrifugal support than prograde material. Simulations by astrophysicist Nicholas Stone in 2012 showed that retrograde accretion can be more efficient at extracting energy from infalling matter. When a supermassive black hole captures a star on a retrograde orbit, the tidal disruption produces different light curves than prograde encounters. Some AGN might switch between prograde and retrograde accretion as they consume material from different directions. In a sense, black holes are ambidextrous, spinning clockwise, yet capable of devouring matter spiraling either way. Quantum hair might allow black holes to retain more information than classically predicted. Picture subtle quantum fields extending beyond the event horizon, carrying information about what fell into the black hole in ways not captured by just mass, charge, and spin. Physicists Stephen Hawking, Malcolm Perry, and Andrew Strominger proposed in 2016 that soft gravitons and photons could provide this quantum hair. These particles carry zero energy but possess other quantum numbers that could store information. The proposal aims to resolve the information paradox without requiring dramatic modifications to general relativity. Other physicists remain skeptical, arguing the proposed hair cannot carry enough information to account for everything consumed by the whole. The debate continues as theorists explore how quantum mechanics and gravity interact at black hole horizons. To think that complexity might hide in the seemingly simple geometry of curved space. Disk-jet connections remain poorly understood despite decades of research. Imagine matter spiraling inward through an accretion disk, while simultaneously jets shoot outward along the rotation axis. Yet the physical mechanism linking these flows remains mysterious. Magnetic fields clearly play a role, but how disk material gets channeled into jets and accelerated to near light speed involves complex physics. Observations of black hole binary systems like GX 339-4 show correlations between disk emission and jet power, suggesting tight coupling. Radio astronomer Rob Fender developed empirical relationships in 2004, connecting jet power to X-ray emission from the inner disk. General relativistic MHD simulations by multiple research groups have made progress reproducing jet formation, but matching all observed properties remains challenging. In a sense, black holes guard their secrets, revealing effects while concealing mechanisms. Gravitational lensing by black holes could create time delays in signals. Consider light from a distant source passing on both sides of an intervening black hole, the two paths having different lengths through curved spacetime. Signals traveling these paths arrive at different times, creating an echo effect. For stellar mass black holes, time delays would be microseconds or less. But for supermassive black holes in galaxy clusters, delays could reach days or weeks. Astronomer restful proposed in 1964, using time delays from gravitationally lensed supernova to measure cosmic distances and test cosmological models. In 2015, astronomers observed supernova restful lensed by a galaxy cluster, creating 4 images with time delays of days. While not directly lensed by a black hole, this technique could work for black hole lenses if alignment were perfect. To think that gravity writes history in multiple copies, each arriving in its own time. Accretion efficiency determines how much mass converts to radiation. Picture matter spiraling toward a black hole, some of its gravitational potential energy converting to radiation before crossing the horizon. For a non-rotating black hole, about 6% of the infalling mass energy can radiate away, while for maximally rotating black holes, up to 42% can escape as radiation. This makes black hole accretion the most efficient energy generation mechanism known, far exceeding nuclear fusion's 0.7% efficiency. Astrophysicists Don Page and Kip Thorne calculated these efficiencies in 1974, showing rotation dramatically affects energy extraction. Quasars powered by supermassive black holes convert mass to light at roughly 10% efficiency on average. This explains how objects smaller than our solar system can outshine entire galaxies containing hundreds of billions of stars. This reminds us that falling itself is power, descent transformed into brilliance. Black hole weather describes variable accretion patterns and outflows. Consider that just as Earth has weather from atmospheric dynamics, black hole environments exhibit variable winds, flares, and state changes driven by accretion physics. The black hole binary, GRS 1915 + 105, shows state transitions where its X-ray emission pattern changes dramatically over hours, cycling through different accretion modes. Astrophysicist Tommaso Belloni catalogued these states in 2000, identifying more than a dozen distinct patterns. Some changes correlate with jet launching, others with disk geometry modifications. Whether near black holes involves magnetohydrodynamics, radiation pressure, and thermal instabilities rather than water and air. Predicting this weather remains challenging despite sophisticated simulations. In a sense, black holes have moods, their dispositions shifting like storms across an event horizon. Entropy of black holes relates to their surface area rather than volume. Imagine a black hole's disorder measured not by the three-dimensional space it might contain, but by the two-dimensional area of its event horizon. Jacob Bekenstein proposed in 1972 that black holes have entropy proportional to their horizon area, challenging the notion that entropy always increases with volume. Stephen Hawking proved this connection quantitatively in 1974 by showing that black hole temperature is inversely proportional to mass, while entropy scales with area. This suggests profound connections between gravity, thermodynamics, and quantum mechanics. The holographic principle, developed by Gerard T. Hooft and Leonard Susskind in the 1990s, generalizes this idea. proposing that all information in a volume of space can be encoded on its boundary. To think that 3 dimensions might be illusion, reality painted on a 2-dimensional canvas. Gravitational wave astronomy could detect cosmic strings interacting with black holes. Consider hypothetical 1-dimensional topological defects from the early universe, infinitely thin yet carrying tremendous mass per unit length. If cosmic strings exist and intersect black holes, they could produce distinctive gravitational wave signatures. The black hole might capture a loop of strings, which would oscillate and radiate gravitational waves at characteristic frequencies. Physicists Xavier Siemens and collaborators calculated in 2006 how black holes could act as detectors for cosmic strings through this mechanism. LIGO and future detectors might find evidence for strings indirectly through such interactions. Alternatively, if strings do not exist, the absence of expected signals would constrain their possible properties. This reminds us that black holes might serve as laboratories for exploring physics beyond current knowledge. Radiation-dominated accretion flows occur when radiation pressure exceeds gas pressure. Picture the inner accretion disk, so hot and luminous that photons exert more pressure than the gas particles themselves. This happens near the Eddington limit, where radiation pressure nearly balances gravity. The disk geometry changes, possibly becoming geometrically thick despite rapid cooling through radiation. Polish astrophysicist Marek Abramowicz and colleagues developed slim disk models in 1988 to describe this regime. These disks exhibit different stability properties and temperature profiles than standard thin disks. Ultraluminous X-ray sources might involve radiation-dominated accretion onto stellar mass or intermediate mass black holes. The physics becomes complex because radiation and matter couple strongly. In a sense, light becomes structural, its pressure shaping the very flows that generate it. Spin measurements of black holes test general relativity in strong gravity. Imagine determining a black hole's rotation by observing how space-time dragging affects nearby matter and light. X-ray spectroscopy of ion emission lines from the inner accretion disk reveals broadening and shifts caused by relativistic motion and frame dragging. Astrophysicist Christopher Reynolds pioneered these techniques in the 1990s, using NASA's XMM Newton and NuSTAR telescopes. Measurements of multiple stellar mass black holes show spins ranging from near zero to near maximal. The spin distribution contains clues about black hole formation and evolution. Each measurement tests whether general relativity correctly predicts how rotation warps spacetime. So far, observations match theory remarkably well. To think that iron atoms, shining in their death throes, map the geometry of spacetime itself. Superkicks from asymmetric mergers might eject black holes from dwarf galaxies. Consider a merger producing a recoil velocity exceeding the escape speed of a small galaxy, perhaps 200 to 300 kilometers per second. The merged black hole would be flung into intergalactic space, orphaned from its birth environment. Simulations suggest that specific configurations of spin and mass ratios produce the strongest kicks. In dwarf galaxies with relatively shallow gravitational potential wells, even modest kicks could eject the central black hole. Astronomer Laura Blecher modeled in 2016 how this process might explain the apparent deficit of black holes in some dwarf galaxies. These wandering black holes would be difficult to detect without accreting material. In a sense, violence breeds exile, the most catastrophic collisions producing cosmic nomads. Gravitational redshift near black holes affects spectral line shapes distinctly. Picture photons climbing out of the deep gravitational well near a black hole, losing energy and shifting to longer wavelengths. For emission from an accretion disk at various radii, inner regions show stronger redshift than outer regions. This creates asymmetric, skewed spectral lines different from simple Doppler broadening. The iron K-alpha line at 6.4 kiloelectron volts becomes a powerful diagnostic tool. Japanese astrophysicist Kazuo Makishima and colleagues first observed these relativistic iron lines in 1995 using the ASCA X-ray satellite. The line profile encodes information about disk geometry, black hole spin, and space-time curvature. Modern X-ray telescopes resolve these features in dozens of systems. This reminds us that atoms remember the depth from which they climbed, their light-carrying maps of curved space. Orbital resonances might affect accretion disk stability and emission. Imagine regions in the disk where orbital periods maintain simple integer ratios, particles completing 2 orbits for every 3 of an inner region. For example, these resonances can create density waves and heating patterns similar to resonances in planetary rings. Astrophysicist Gordon Ogilvy proposed in 2001 that resonances might contribute to quasi-periodic oscillations observed in black hole X-ray emission. The resonances could occur between different fundamental frequencies of disk oscillation modes. Testing these ideas requires precise measurements of multiple simultaneous frequencies. Some black hole systems show frequency ratios suggestive of resonant phenomena.